Hi, I'm Ilan Moyer, a PhD student in mechanical engineering at MIT. Today I'll be sharing our work exploring craft-aligned approaches to digital fabrication design in our paper titled Don't Mesh Around, Streamlining Manual Digital Fabrication Workflows with Domain-Specific Scanning. This work was done in collaboration with Samuel Bourgeot, Devin Frost, and Jennifer Jacobs of the Expressive Computation Lab at UCSB. Our research builds on the digital pottery wheel, or DPW, which we introduced at CHI earlier this year. The DPW is a traditional throwing wheel augmented with 3D printing capabilities. We imagined that clay 3D printing preceded CNC technology and wondered what form factor and approaches it might take had it descended from existing ceramic practice rather than industrial modes of production. The result was a polar coordinate 3D printer that uses the rotational axis of the wheel for printing. This harmonization of new and old about a shared axis enabled several new craft-centric digital fabrication workflows, such as throwing on a printed form, printing on thrown forms, as well as meaningful real-time manual control of the printer through what we call Pot Assist. We developed a complementary control system for the DPW that imagines motion control signals as audio-like streams that can be synthesized, transformed, recorded, and played back in an architecture similar to a modular synthesizer. By using standard step direction signals for these streams, we remain compatible with existing G-code-based infrastructure while not being limited by it. While we succeeded in blending manual and conventional digital fabrication approaches in this earlier work, we still use digitally designed forms as a starting point for the majority of the DPW workflows. For craftspeople, the question remained, how do I design for digital fabrication systems? Do I need to leave my work, sit in front of a computer, and learn CAD software? We see an opportunity to support skilled material design in digital fabrication by developing material-first, hands-on digital design workflows and to create domain-specific representations that streamline the transition between digital and material domains. We again turn to the nexus of our system, the rotating wheel, for inspiration. To explore this for clay 3D printing, we introduced the Craft-Aligned Scanner, or CAS, a single-point laser-based scanning system that allows objects designed using traditional wheel-throwing techniques to be directly converted into spiralized 3D printing toolpaths for digital fabrication. Before I dive into how the CAS works, I'll explain a bit about the constraints of clay 3D printing in relation to existing 3D scanning methods. Because of the relatively fluid nature of wet clay and the mechanisms that typically are used to extrude it, ceramic 3D printers can struggle with starting and stopping flow. This means that toolpaths for clay 3D printing tend to be one continuous spiral. In contrast, typical 3D scanning workflows generate a surface mesh by measuring point clouds using a variety of methods, which then need to be cleaned and sliced to generate a toolpath. This traditional approach is generic and can require significant computer-based labor to achieve good results. So let's dive into how the CAS approaches this problem in a domain-specific, craft-aligned way. The heart of the CAS is a laser distance sensor aimed at the center of the wheel and mounted to a vertical elevator. The process starts when the ceramicist who throws a form using the DPW in wheel mode. They then position the laser at the bottom of the form using up and down buttons on the CAS interface. They initiate the scanning routine with the start button. This causes the wheel to start spinning and the elevator to begin lifting in sync with the wheel, tracing a spiral path on the form with the laser. By choosing a spiral pitch equal to the layer height, the resulting scan can be directly stored as a 3D printing toolpath that will reproduce the scanned form. This allows us to circumvent the computer-based post-processing steps typically needed to work with traditional mesh-based scanning approaches and keeps the practitioner at the wheel instead of at the computer. Because the scan data is synchronously stored in the same step direction format used to control the wheel, it is available for immediate playback by pressing the play button. In order to maintain compatibility with the DPW control system, we directly record the scan data not as absolute coordinates, but as step direction motion streams comprising the printed toolpath. This format introduces some interesting challenges. In order to convert scan data into recorded toolpath motion streams on the fly, the process happens at a nearly constant linear print speed rather than a constant rotational rate. For example, at the beginning of the scan, the print arm needs to move to the radius of the vessel, so the wheel stays stationary as the scanner records purely radial motion. Something similar happens if the scanner encounters a radial step in the object. To support this, we buffer the scan data and feed it into a toolpath generator. It is the virtual motion of the generator that gets recorded. As the buffer grows, we slow down the wheel to allow the generator to catch up. Scanning and toolpath recording thus happen in quasi-real time. Another benefit of using synchronous motion streams as the lingua franca of our control system is to enable real-time manipulation of the scan toolpath while printing. To explore this further, we developed a texturizer module, which sits between the scanner module and the rest of the DPW control system. As the wheel spins, the texturizer overlays an oscillating motion of the print arm onto the toolpath being played. We provide several controls over this pattern via knobs on the texturizer control panel. Number of waves sets the spatial frequency of the pattern. Width sets the amplitude. Shift adjusts the phase shift between successive layers, allowing for a weave-like pattern. And finally, fade allows the amplitude to fade in and out and even invert along the height of the print. Because the texturizer operates directly on motion streams as they are being played, all controls are immediate and latency-free. Our approach allows practitioners to augment scan forms with a popular and distinctly digital affordance of ceramic 3D printing surface texture in real time and without touching a computer. While our primary aim was to support digital fabrication design without a desktop computer, our approach can also support novel workflows that incorporate and streamline desktop CAD. We created a despiralizing algorithm that allows the toolpath to be used as a starting input to action-oriented design software such as CoilCam. We believe that starting with handmade forms may be a promising approach to providing practitioners a jumping-off point into computer-based CAD software. To evaluate the CAS and texturizer, we commissioned Isaiah Porter, a production potter with 10 years of experience, to produce manually thrown vessels as an input to our system. We then used Isaiah's thrown vessels and 2 other pre-existing forms to explore affordances of the CAS and texturizer system. We started by directly reproducing Isaiah's symmetrical thrown forms with 3D printing. We found that the results closely mirrored the starting forms, with slight diameter differences due to the compression of the wet clay. We also reproduced asymmetrical forms, including a vessel with a hand-formed spout. In this workflow, we scanned just the spout from Isaiah's original vessel and placed it on top of another thrown form. The relative nature of the DPW control system helped here, as we were able to match the print diameter to that of the thrown form by manually adjusting the radius in real time with the DPW's control lever. We also ran experiments with the texturizer, such as scanning Jeff Suina's asymmetrical 3D printed vessel and then reproducing it in a tightly woven surface texture in its middle portion. Here are some other examples of modifying scans of Isaiah's vessels with real-time control of the texturizer. In this first piece, we printed from a scan and then introduced the texturizer midway through. Jennifer then manually smoothed the untextured portion using the DPW in wheel mode like a traditional pottery wheel. This vase in particular was interesting to us because we accidentally discovered that the fade feature could result in an inversion of the texture partway up the vase when the amplitude went negative. These sorts of happy coincidences help to build an expressive palette of creative possibilities for the system. As one last example, I'd like to show you results from the computer-based workflow where we took a starting form scanned on the wheel and used it as the base form for digital manipulation in CoilCam. While this workflow currently still requires software expertise, it enables a wider range of possibilities than what can currently be conceptualized just on the wheel. We discuss how methods like CAS may impact craft and digital fabrication in detail in our paper, but in the time remaining, I'd like to briefly touch on the key implications of our work. Practically speaking, the ability to directly reproduce existing ceramic forms may have implications for production pottery. However, we believe that the furthest reaching implications of the CAS and DPW as a body of work are as a general approach to building digital fabrication tools. We started with the physical metaphor of the pottery wheel as a way of anchoring a relatively new fabrication technology to an existing, well-developed practice. This led us to a polar coordinate system, which not coincidentally aligns with the way of thinking about making ceramic vessels. From here, operations that were difficult to both conceive and execute in Cartesian space, such as offsetting a digital form while it is printing, become trivial simply by adding or subtracting a little bit to the radius. Similarly, tracing a spiral with a laser to scan an object fell naturally out of our coordinate system and aligned naturally with the spiralized way clay 3D printing wants to work. Our experience has been that when you find a mental model that resonates with how people are already thinking and doing things, happy coincidences can start to occur almost spontaneously. Our development methodology has been to simply follow the implications of the form factor wherever it may lead us. In doing so, we are supported rather than led by the affordances of modern technology. We believe that this pattern may be applied to many other domains of digital fabrication. In conclusion, when developing new digital fabrication tools for skilled use, we urge you, don't reinvent the wheel. Thank you.
All right, we have much of time for questions. If you have questions, please line up behind the mic in the center.
Thank you so much for this just really amazing body of work. Could you say a little bit, so here everything is based on a cylinder essentially that's sliced in like traditional kind of XY layers.
Mm-hmm.
Do you have any thoughts about kind of breaking out of the XY plane and whether you could do non-planar type geometries both in scanning or printing?
Yeah, that's a really interesting idea, and not one, I can't speak to my collaborators, not one I've given much thought to, how to print kind of in almost 3D space. The scanning has some interesting constraints because it's a laser sensor. For example, that spout, we had to stop the scanning when we kind of reached the water level where it would start to spill out, because otherwise the scanner starts reading negative radii and gets very confused. So I think that's inherent in the scanning approach. But as far as the printing, that's something that would be very interesting to explore. Yeah, thank you for that. Okay.
No. Any other questions? We still have time.
Okay.
All right.
I've left all this time for questions.
If no question, I have a question. So it's very interesting to see the last slide, which has a nice workflow, right? So I'm wondering about the artifacts into space, which is the last step. Mm-hmm. Can you elaborate more about like what kind of applications can be benefiting from this approach? For example, interactions. I can imagine something about sensing or other feedback you can provide and embed in the pottery artifacts. So do you have anything? Ideas about the future applications?
Oh, interesting. Yeah, that's a good question. I mean, I can speak to what sorts of artifacts have emerged in the past from explorations we've done, where, let me think how to answer that. Yeah, sorry, off the top of my head, that's a tough question.
I just wonder, because this is a very nice workflow, and we can create multiple different geometries, and we can easily help the novices to quickly create this pottery design, and there's a lot of potential to embed more interactions in these artifacts. So that's just my wonder.
Interactions in the artifacts themselves.
Yeah.
Interesting.
All right, I think we are about the time, so thank you. Let's give a round of applause for Ilan.